What up, y'all? Welcome back. We're talking about the coupled pendulum problem. Remember, in the description of this problem, we have these two pendulums that are fixed to a stable support structure. Each pendulum consists of a inextensible massless rod. We measured the length of each rod. In the two pendulums, those lengths are the same. At the bottom free end of each rod, we attach a mass. The mass of the first one is M1. The mass of the second one is M2. Then we take an extension spring and connect each end of the extension spring to either mass. When we're ready, we put one of the masses in motion and then watch the entire system move back and forth in interesting ways. The coupled pendulum problem is to predict the exact location of each center of mass along the ruler, given only information about the length of the pendulum, the masses themselves, and also the spring constant. In previous videos, I claimed that we can transform the problem of predicting the location of each center of mass into a standard eigenvalue problem in the form a times x equals lambda times x, where we're searching for both the scalar lambda and the vector x. That process of translating the real problem into a mathematical ideal problem is known as mathematization. For the coupled pendulum problem, we're going to have 5 steps with some substeps to mathematize that problem. The first thing that we're going to do is study the dynamics of a single pendulum that is not connected to anything else. In other words, when studying a very hard problem, we break that problem into pieces. The first steps that we focus on should make simplifying assumptions so that we can get our head around the individual components that we're looking at. With that in mind, our first simplification is just to study the dynamics of a single pendulum. Once we've done that, we're going to formulate a modeling framework for the coupled system of masses by introducing proper variables and notation. Once we get our head around how each pendulum moves individually, we're going to start introducing notation in the system to express that study using mathematical variables. At this stage in the game, we're going to combine our understanding of the dynamics of the simple pendulum with the mathematical variables that we generated in step 2, and we're going to look at net forces on each mass using something called a free body diagram. These free body diagrams give us a visual representation of net forces. That's really powerful because there's a famous law in physics known as Newton's second law that says the net force on any object is equal to the mass times the acceleration. But acceleration is the second derivative of displacement, or movement in position, which means we can relate the net forces we got from step 3 to some set of coupled ordinary differential equations that describe the motion of our system, which is what we do in step 4. In other words, in this stage, we're going to have a set of equations that involve functions and derivatives whose solution is the description of the position of each mass. Once we have those differential equations describing the motion of each mass as a system coupled together, we're going to transform that into a standard eigenvalue problem by creative use of matrix and vector notation. These 5 steps will play a crucial role of translating our original coupled pendulum problem, which is a real world problem that we can measure, into the corresponding standard eigenvalue problem. In the next video, we'll get started with step 1. I'll see you there.